Hello again. This is Chem 121, Chapter 3. In this lecture, I'm going to do sections 3.5 to 3.7. So in sections 3.1 to 3.4, we were introduced to the subatomic particles that comprise the atom. We looked at atomic number and mass number. In section 3.3, we looked at isotopes and atomic masses. And in section 3.4, we were introduced to the periodic law and the periodic table. In sections 3.5 to 3.7, we're going to look at how electrons are arranged in atoms and look at something called electron configurations. And finally, look at the electronic basis for the periodic law and the periodic table. So there's a nice link here, orbitals and electron configurations for Khan Academy. In an earlier section, I talked about the fact that when scientists first arranged elements in the periodic table, they put them into the vertical groups based on their similar chemical behavior. And I talked about how later on in the chapter, I would talk about what the basis was for this similar chemical behavior. And I also mentioned earlier that chemical behavior of elements is really based on their electrons. The identity of elements is based on the number of protons, but their chemical reactivity is based on electrons. That's because in chemical reactions, the nucleus doesn't really participate. It's only the electrons that are involved in chemical reactions. When the nucleus gets involved, we tend to get things that release huge amounts of energy. So common everyday chemistry is really the chemistry of electrons. The nucleus doesn't really get involved in chemical reactions. The nucleus is what gives us the identity of atoms, but it's really the electrons that are involved in reactions. So if we think of the space around the nucleus as a series of shells, as depicted in this picture, the higher energy electrons occupy the higher shells. So this electron out here is in a higher shell than these two electrons. So this electron has a higher energy than these two electrons. So the shells in this diagram actually correspond to the periods in the periodic table. So these two electrons would be occupying the first period in the periodic table. And this electron would correspond to the second period in the periodic table. So the first two electrons that go into an atom represent electrons that would go into an atom that would be in the first period in the periodic table. And the next electron that gets to an atom would represent electrons that got added in the second period in the periodic table. And I'm going to show you how that works. So inside the shells in that diagram are subshells that are divisions of the shell. And it's kind of hard to show it in this diagram. So you just kind of have to imagine subdivisions of these larger shells. And each subshell can hold a different number of electrons. So here's the first four shells, and you can picture these as the first four periods in the periodic table. And inside those four shells are these different subshells. The first shell only has a single subshell called S. The second shell, or the second period in the table, has these two different subshells designated S and P. The third shell, or the third period in the table, has these three subshells, S, P, and D. And the fourth, we're only going to go up to the fourth shell, has these four subshells designated S, P, D, and F. And the different shells can basically hold different numbers of electrons. The S shell can hold 2, the P shell can hold 6, the D shell can hold 10, and the F shell can hold 14. And I'll show you how we use these shells and subshells to build up the electronic structure for atoms, how we add the number of electrons to atoms. So depicting the electronic structure of an atom, we can draw a picture like this. We can just show that this atom has 3 electrons, 2 in the first shell and 1 in the third shell. But there's also a shorthand method that we can use called an electron configuration. So for a really simple atom like hydrogen that only has a single electron, and we know that hydrogen has 1 electron because it only has 1 proton. So we can use this shorthand method, which is called an electron configuration. So we know that this single electron in hydrogen is going to try to be as close to the nucleus as it can possibly be. So it's going to be in the very first shell. If it was a picture like this, it would be in this very first shell, as close to the nucleus as it could get. So that's what this number 1 represents. It's going to be in the S subshell, because this first shell actually only has an S subshell. And we're going to put this 1 up here to indicate that hydrogen only has a single electron. So if we read out this electron configuration, we would say 1s1. If we go to the next element in the periodic table, helium, now helium is still going to put electrons in the first shell, but now it's going to have 2 electrons, first shell, S subshell. So we would write that electron configuration as 1s2, first shell, S subshell. And then we just continue on in the table, adding electrons to the next subshell or the next higher shell. So when we get to lithium, we've actually run out of room in the first shell. So you can see we put 2 electrons into the S subshell, so the first shell is all full. So if we want to add more electrons, now we have to go up to the second shell. So for the third electron in lithium, we go up to the second shell, and we're going to put electron in the S subshell. So for lithium, we write a single electron in the second shell in the S subshell. For the lithium, which has 3 electrons, we would put 2 in the 1s and 1 in the 2s. And we would read it out by saying 1s2, 2s1. And then if we just keep going in the periodic table, beryllium has 4 electrons. We would put 2 of them in the first shell and 2 of them in the second shell. 1s2, 2s2. Now, if we wanted to keep going past beryllium in the periodic table, we see that we filled the first shell, we filled the S shell of shell 2, because S can only hold 2 electrons, that's 4. So if we want to go past beryllium, we have to start now using the P subshell of the second shell. And that's exactly what happens past beryllium. Once we get to boron, if we want to add the next electron, now we have to start adding electrons to the P subshell. And notice these are just the elements that come after boron in the second shell of the periodic table. Each successive element has to add 1 additional electron because we're adding 1 additional proton as we move across the table. So we're just going across the second period, filling up the P shell. When we get to the end of the second period, now we can see that we filled up the second shell because we filled the S subshell and the P subshell. So if we want to add any more protons or any more electrons, now we have to go to the third shell. And that's exactly what happens when we get to sodium. Sodium has 11 electrons. We put 2 in the 1s, 2 in the 2s, 6 in the 2p, because that's all that p can handle. 6 plus 4 is 10, and the 11th electron goes into 3s. And we can just keep building electron configurations like this all throughout the table. I'm not really going to have you do that in this class. The reason I wanted to show you how we build electron configurations is because I want to use electron configurations to show you why the different groups in the table have the same characteristics. And it's this right here that we're looking at. Notice there's a single electron in the outermost shell for sodium. a single electron in the outermost, it's also called the valence shell. Single electron in that outermost, or the third shell. So when scientists first arranged the elements in the periodic table, they put them into groups based on their behavior. And the question was, what was the basis of this similar behavior? Well, it turns out if you look at all of the elements in group 1A and you look for what they have in common, every one of those elements has a single electron in its outermost shell. So we know that for lithium, we have a single electron in the 2s shell. And now we've built the electron configuration for sodium, and we can see that it has a single electron in the 3s shell. If we kept going in the 4th period and built the electron configuration for potassium, we would see that potassium has a single electron in its valence or outermost shell. Similarly, for group 2, beryllium had 2 electrons in its outermost or 2s subshell. Magnesium has 2 electrons in its outermost or 3s subshell. And if we kept building the electron configurations in the 4th period, we would see that calcium has 2 electrons in its outermost or 4s subshell. So what group 2 has in common is 2 electrons in its outermost shell. And what group 1 has in common is 1 electron in the outermost shell. If we look at group 6A, we can see that there are 6 electrons in the outermost shell. The outermost shell being shell 2. 2 plus 4 is 6. The next period down, period 3, in group 4 would be sulfur. And sulfur also has 6 electrons in the outermost shell, that shell being shell 3 now. 2 plus 4 is 6. If we go to group 7 and we look at fluorine, we can see that fluorine has 7 electrons in its outermost shell. If we go to the 3rd period and look at chlorine, which is in group 7, we can see that chlorine has 2 plus 5, or 7 electrons in its outermost shell. The reason that elements in the same group have the same chemical properties is because they have the same number of electrons in their outermost or valence shell. This is only true for A group elements. So all of the elements in group 1 have a single electron in their valence shell. All of the elements in group 2 have 2 electrons in their outermost or valence shell, and the number of valence electrons is equal to the group number. All of the elements in group 5 have 5 electrons in their outermost shell. All the elements in group 6 have 6 electrons in their outermost or valence shell. So that's the basis for the fact that elements in the same group have the same chemical behavior, because we found out in this section that chemical behavior is based on the electron structure of atoms, not their protons or neutrons. Okay, that's all for sections 3.5 to 3.7.